So, from stationary phase, we have this very nice result for the position of a wave packet. And the idea now is to ask ourselves, we've seen we can make a wave packet. Here, I'm going to kind of draw what my wave packet's doing. I'm drawing a picture here of psi of x and t. The probability is directly related to it. But we can make a thing that's localized with a certain width here, delta x, right, with its peak here at this position, which I guess I could call x or x max. That's what this x is, the position of this maximum. And that position then will move in time. And our goal now is to see what we can learn if we try to insist that the packets that we construct always track the position of a classical particle. So I want now to make a series of connections that will allow us to ensure that this packet and this particle are always going to move together in unison. Now for that to happen, I want to think about the connections that we're making. So what we're saying is that the velocity of the classical particle, if I think of it as having a trajectory x of t, the velocity of the classical particle, which I will call x dot, must match my group velocity. That's what I've been saying so far, right? This is going to ensure the correspondence principle, so that the probabilities are such that what I will most likely observe is exactly just the motion of a classical particle. Now the next connection we can make is that this group velocity is the famous d omega dk, group velocity formula. And we've just now established this mathematically using our method of stationary phase. So that's pretty rock solid. Now, we know something about the wave vectors because we know about the wavelength, right? But we still don't know what frequencies we need to associate with our waves in order to get them to track the classical particle. So let's get this into our more familiar language. Remember that omega is 2 pi times these frequencies nu that we've been thinking about. And then k, remember, is 2 pi over lambda. So this is somewhat nomenclature. This is also just, standard wave physics, right? Standard wave physics can make this connection for us. And there's a little bit of, I'm sorry, k is not 2 pi over k. K is 2 pi over lambda, getting it into sort of standard wave terminology. Now, of course, you can see the 2 pi's will cancel out. So I've got 1 over lambda in the bottom. Let me just rewrite that. So that's d nu d 1 over lambda. Now here's where things get interesting. What we know, here I'll just include that in there because that was just a little bit of rewriting the math. That's still coming from our standard wave physics. Now remember what we know for, say, electrons or nuclei, right? We know that lambda directly from experiment is h over p. That comes to us from experiment. We don't really have a choice in designing our wavelengths. So 1 over lambda, if I substitute in, you see, will be d nu d. 1 over lambda is p over h. Right? So this connection here, that is actually what came from our electron physics, right? Here, I'm going to try that one more time. Sorry, guys. I had to make a slight adjustment to my diagram. And I think I can just move him over here a little bit. Oh, that's kind of fun, right? That comes from experiment. Lambda equals h over p. That came from the experiment. And now, finally, I can rewrite this one more step because it makes an interesting connection. This h, I can move on top. So I've derivative of h nu. Oh, well, that should sound familiar. That's a combination, h nu, that we've seen for the photon. That's kind of neat. dp. So, what we've learned so far is there's something out there that's directly related to frequency, And I want things to be so that its derivative with respect to momentum always gives me, right, the velocity of the classical particle, right? So the question now really becomes, is there something in classical physics whose derivative with respect to momentum, so I'm looking for some kind of classical physics here, whose derivative with respect to momentum gives me always the velocity of the particle. If there is such a quantity, that's beautiful, because then I can solve the mystery of what frequency I should attach to my waves. Because whatever that quantity is, I should set it equal to h nu, and that will guarantee through this chain of logic that I will then have wave packets that travel along with their group velocity exactly matching the velocity of the classical particles. So I'm very motivated to know what this function is. And we know two other things about this function, right? One, right, we know that it must be written in terms of momentum. And the second thing is we know what type of quantity it is. H nu, remember, is the formula for the energy of a photon. So just from units, I know it has to be some kind of an energy. And it turns out there is such a quantity. It's something called H. It's something called the Hamiltonian of the system. You may not have heard of this yet, but this features in very prominently in advanced classical mechanics classes. So this would come up in your, for instance, your Phys 3314 or 3318. And what the Hamiltonian is, literally, it is the that's the Hamiltonian, and it is the total energy of a particle that means, of course, the kinetic energy, which I usually call T, right, plus the potential energy V. So it's the total energy. But there's a very important stipulation written in terms of the momentum. So it's exactly what we are looking for, right? I need something that's written in terms of momentum so that I can take a partial momentum derivative. And I need something that is units of energy. And there is exactly this quantity. And if I select my frequencies nu so that h nu gives me my Hamiltonian, I exactly recover the correspondence principle. My wave packets can track my particles. So the conclusion of all of this is that for the electrons, we now know what h nu is. It's equal to the Hamiltonian of the system. With the Hamiltonian defined, exactly as I have defined it for you up here. Now, I'm sorry, that's a little bit sloppy. So Hamiltonian. It's so important, I want to get it written down just right. Right. So h nu equals h. Beautiful. Okay.